We're delighted to introduce our first speaker, Dr. Jacopo Taddeucci from the National Institute of Geophysics and Volcanoes from Italy, with his talk, The Hard Life of Pyroclasts, in Between a Break and a Rest, It's a Blast.
Hello to everybody. I hope you can hear me. I mean, it's an unusual situation. It's a great honor to be here in my room, in my house, but talking to all of you, and it's really great thing and a great effort what you have been putting on. It's an honor to be at this symposium. And I really hope to be able to come to Liverpool, not too late, to see you all in person. So now, if I just succeed in sharing my screen properly and in running the presentation properly, I can go. Okay, there we go. So, yeah, the hard life of Pyroclast in between a break and a rest. It's a blast, this life. And this is why I'm the only one here wearing the helmet. So let's begin. In the beginning, there was magma. And magma broke. And then there were pyroclasts. And pyroclasts were small, and the airplane couldn't fly. And the pyroclasts were large, and unfortunately, people died. So now let me introduce to you a pyroclast. Yes, this is a tiny piece of volcanic ash from Stromboli volcano, and it's got its name from the Greeks, of course, and actually from the Greek word for fire, which is pyros, and the word for fragmental, this is klastos. So pyroclast literally means broken by fire. And this tiny piece of ash has larger cousins, which include pumices and volcanic bonds. One key features of pyroclast in general is the huge span of sizes that they can have. So the size of pyroclasts can span from less than 1 micron, like in this picture here, this tiny particle here, which is about 100 times smaller than a human hair, to more than 10 meters, like this block here on Etna, which is about the size of a lorry. And this is crucial for the whole rest of the talk, as we will see. The fragmental origin of pyroclasts is evident by the simple fact that they are fragments, they are clasts by definition. And also pyroclasts are very important because they hold us information about the parental magma from which they fragmented. For instance, in this particle here, it's quite evident that the parental magma was having inside it bubbles of gas. And if we slice open one pyroclast, we can have even more information about the magma from which it generated. So as we were saying, the magma was having gas bubbles here in black, and then was also having crystals inside it. So these dark geometric shapes and also the brighter geometric shapes. And all in between the crystals and the bubbles is now glass and was once hot molten glass. Magma indeed is a multi-phase mixture of gas bubbles, solid crystals, all dispersed in high temperature molten glass. And then the magma fragments. And the magma, despite its molten states, fragments as a brittle bottle of glass would do. And here we have crystals, tiny crystals, that got caught in the fragmentation, but is still immersed in unbroken glass around it. This other image can help us solve this mystery. Also here we have crystals that are clearly broken by the fragmentation, but we also see these tiny wisps of white material going from one crack to the other. And these tiny wisps are the remains of the cracks that fragmented the magma. The point is that the magma, being a high temperature glass, can heal in the same way as two pieces of honey, for instance, they heal together when touched. So the point is that the cracks propagated through the melt, they broke the melt, they broke also the crystals, but the melt could heal because being at high temperature. The crystals, being solid, couldn't heal at all. The evidence that we have is that up fragmentation, we have a network of cracks that propagates all through the magma. We have larger cracks that are able to isolate pyroclasts from one another, but the smaller cracks just succeeded in breaking the crystals and then healed up. A key point of this process is the fact that the cracks liberate the gas that is pressurized inside the bubbles. And this gas is now free to expand. And the expansion of this gas is what drives the explosion that then looks just like this. This is an explosion of saturation overflow. So for the rest of the talk, I think it will be useful to try to recollect what are the forces at play when a pyroclast is ejected out of the volcano. Of course, important and first of all is gravity. Sorry, give me a second. Let's see if I can do this. Okay. Gravity is important, of course. All the pyroclasts that are ejected out of a volcano are subject to gravity. None of them goes to outer space. And so all the pyroclasts ejected sooner or later will fall back down. Now it's important to remember that gravity is not a force. Gravity is an acceleration. So when gravity is the only force at play, an object will keep on falling under the constant acceleration. So its fall velocity will increase constantly over time. But our pyroclasts are not being erupted on the moon. They are being erupted on a planet that has an atmosphere around it. And a body which moves in a fluid is experiencing a friction against this fluid, which is called a drag, and resulting is a drag force. So when an object is falling subject to gravity through a fluid, it experiences the drag. And when the drag force is balancing the momentum induced by gravity, this object keeps on falling at a constant velocity, not at a constant acceleration. And this constant velocity is called the body's specific terminal fall velocity. Then, if instead of falling, the pyroclast is rising through the air, for instance, hurtled away by an eruption, its rise is driven by momentum, but is contrasted by drag with the fluid and by gravity, which is pulling it down. But the pyroclast is being hurled because it's entrained in a jet of gas, of volcanic gases that are liberated by fragmentation. In this case, things change. And what we have is that the gas is not actually slowing down the pyroclast, but the drag is actually driving and pushing the pyroclast. And this is working against gravity. And the pyroclast is hot, so it's exchanging momentum with the atmosphere and the gas surrounding. And also the pyroclast is freshly broken. That means that it has fresh surface and can liberate electrical charges with the surrounding. So which one of those forces will be dominating in controlling the motion of pyroclast mainly depend on the size of the pyroclast. Remember, these sides can be everywhere in between a bacteria and a wave. In reality, then, our pyroclast is not alone at all, and is colliding and exchanging momentum with other pyroclasts because it's in a jet that contains other particles within it. And this jet is also entraining gain, and the processes that are really actually in a concentrated concentration of pyroclast and volcanic gas is really complicated. In the end, what we end up having is this, a volcanic eruption. Now, this is a very accurate representation of a volcanic eruption. Actually, it's an eruption of Vesuvius Mons, close to Naples, and is drawn in 1771, if I remember right. Yes. So what we see here is a jet of gas and particles being erupted by a vent on the side of the cone. And then we have the smallest pyroclast, the volcanic ash, that forms a buoyant plume that winds blows toward the city of Naples over there. Then we have larger pyroclasts, like this one and this one. And these bombs follow ballistic trajectories and fall back here on the sides of the cone. And then there is a lava flow that is flowing from the same vent, and it's getting cooler and darker the more it moves farther away. So this is a very accurate and precise representation. And another interesting points, or actually 2 points in this representation, is the first, that we have here volcano tourists. Yes, let's walk our dog over to the lava. Very safe, extremely. But volcanoes has always been fascinating and will always attract tourists. The other interesting point is that there is a volcanologist in this picture. Can you spot him? Here. This guy here is Monsieur Voller, is the one guy that is actually drawing the painting that we are looking at right now. But his problem, his biggest problem, is that it's hard to convey in an oil painting the fast dynamics that characterize all explosive volcanic eruptions. And to overcome this problem, we no longer rely on oil painting for documenting explosive eruptions. In fact, we are depicted here on ECTA with a high-speed camera and ABI multiparametric fast recording multidisciplinary instrument. And we also now wear a hat instead of a tricorn hat. So armed with these instruments, we visit several volcanoes around the world to get high-speed images of volcanic eruption and track down the motion of pyroclast. This explosion of Sakurajima volcano, for instance, was filmed at 500 frames per second from about 3 kilometers of distance. This explosion resulted in a plume that was 4 kilometers high above the summit of the volcano. And you will see that multiple jets are visible, each one producing vortexes of dark ash and also ejecting bombs that will start to fall around the volcano. And the electrically charged ash particles may produce lightning, you will see. And also quite noticeable is the formation of craters where bombs will impact here on the sides of the crater, and the updraft of the air that is sucked in by the uplift of the volcanic plume over there. So there we go with the video. Now let's move to a somewhat smaller eruption. And this one is still 500 frames per second. The whole video in nature would last about 3 seconds. And this was filmed at Batutara volcano in Indonesia. There we go. I would like to draw your attention to this granule here. I hope you can see my pointer, which is about the size of a small house. And then with even smaller eruptions, we can get closer to the volcanic vent. And this increases the resolution that we can have in the videos. So like here, the smallest particle that we can see are about 1 centimeter or slightly less. In this video, brighter particles are hot while darker ones are colder. You will see the explosion starts with a slow ejection of small pyroclasts and then followed by a more violent explosion. And in this large explosion, plastically deformed car-sized volcanic bombs leave the vent relatively slowly, while smaller pyroclasts will be seen flying faster. There are not just pieces of magma, not just strictly speaking pyroclasts derived by magma fragmentation, but also pieces of rock that are caught in the explosion, and they are colder. And you will also see the high-speed camera starts to shake at some point, and this is due to the fact that the shock wave from the explosion is hitting it and making it shake. And then something different will happen. The explosion will change and will be much richer in colder particles and dense with volcanic ash. So there we go. Oh, this is Yasur volcano in Vanuatu Republic anyway. All right, so now there is much interesting science that we can do with these high-speed videos. The first thing that we started to do was to track the particles right when they leave the vent, just like this. So each set of dots is one particle that we were tracking, and we were focusing on the fastest particles. And the first discovery that we did is that the ejection velocity of particles has nothing to do with the size of a volcanic eruption. So these videos were taken at relatively small, really bonsai volcanic eruptions. And still we were able to measure small pyroclasts leaving the vent at velocities up to 500 meters per second. To give you some context, 500 meters per second is about 1.5 times the speed of sound. Then another very interesting observation that we did is that the ejection velocity of particles at the vent is not steady state at all. Rather, pyroclasts are ejected in pulse. So in this plot, what you're seeing is the ejection velocity of pyroclast over time, and one single dot is one pyroclast. And you see that there are strong fluctuation in the ejection velocity of pyroclast. In this case, between 300 and less than 50 meters per second. But what is interesting is these events here, in which it seems that the velocity of the pyroclast at the vent decays very fast over time. And we call these ejection pulses. And in ejection pulse, the first pyroclast leaving the vent leaves the vent very fast, and then the exit velocity of other pyroclasts goes down and down until the last pyroclast of the pulse is ejected pretty slowly. And each one of these ejection holes actually represent the liberation of a pressurized pocket of gas that is residing inside the magma in the conduit. And how do we know this? We know this because we reproduce these impulses in the laboratory using a shock tube. Now, basically, a shock tube is a pipe which is open at one end and divided in two parts by a diaphragm. What we do is we fill the lower part with pressurized gas until a certain pressure differential is reached, and above the diaphragm, we put at rest some natural pyroclast. Then, by bursting the diaphragm, what happens is that the gas expands, and this expansion is dragging away the pyroclasts that are accelerated and ejected in a way that we think is similar to what happens to the volcano. So in this video, you are looking at the very top exit of the upper part of the pipe, and you will see the pyroclasts coming out in the jet of compressed air, and you will see that they slow down, their exit velocity slow down over time. So not only one single pyroclast slows down while flying, but the velocity of the pyroclasts that are ejected progressively gets slower, like this. Now, this decreasing velocity is due to the fact that the pressure differential that is driving the particles is also decreasing over time. And when we measure the velocity of the particles exiting the shock tube, so this is the velocity and this is time, what we see is that we have the same kind of decay that we have also in the natural volcanic eruptions. And we think that these pyroclasts are really the fundamental units of all explosive eruptions. And how they evolve tells how the eruptions evolves on a sub-second temporal scale. So in these graphs here, we have three different explosions. And these three explosions lasted about 30 seconds or less. And for each explosion, we are tracking the velocity of the pyroclast at the vent, and their ejection angle with respect to the vertical, the size of the pyroclast, and their mass over time. And these three plots depict different explosions, and you can see the pulses over here a little bit and how they define the explosion. Sometimes you can see them better and sometimes worse. But the best way to really get a touch of these explosions and how the pulses define them is by hearing the pulses actually. And so what I did is to sonificate these plots. And to sonificate the plots, basically what I did an audio file, and in this audio file, the tone is proportional to the velocity of the particles. And the loudness, the volume of the audio file is proportional to the mass of the particles that were erupted in one small time window. So when you listen to this, be careful. This is not the sound of an explosion, but is an auditive representation of pyroclast ejection. Now, let me check only one thing. Okay, yes, let's go. So this was one explosion, and now we listen to a different one. And finally, a third one. Okay, I really hope that you could hear anything, that there is somebody out of this room listening to me, but I am confident that if something went wrong, I would somehow know about it. So in this way, you recognize that the ejection pulses very clearly, and it's also quite intuitive to understand how the different combination of pulses with different ejection velocity, duration, and load of particles really defines the feature of the different explosions that we were listening to. And now that I've made you listen to the plots, I want you to listen to a real sound of an explosion that's stronger. And now that you have heard one explosion, actually you're still hearing explosion, I will show you the acoustic waves in videos. So in these three videos, on the right hand is the original high-speed videos, and you can see a beautiful pyroclast leaving the vent and also the ash. On the right hand, I removed any static background for the video. So what you are seeing is just an emphasization of what is moving in the video. And you still see the pyroclast, but you can also see the acoustic waves generated by the explosion. And these acoustic waves are visible because they make small changes in the density of the gas and also in their refractive index. And so they are distorting the light a little bit. So the sound that you heard and you're looking at is a kind of specific volcanic sound, and it's volcanic jet noise, and it's the sound produced in the same way as rockets or jet engines produce sounds. And it's telling us that the jet of gas and pyroclast out of the vent was supersonic during routine. Now, acoustic recording is an important way to monitor an eruption even from far away or when we cannot have direct visibility of the vent. And this video helped us a lot to interpret correctly the sound and the explosions. And these are graphical representation of the explosion. So here we have a classical acoustic track of the explosion, and below we have the frequency distribution of the explosion over time. So in red, we have where the dominant frequency was of the explosion at that time. And the high frequency sound that you were listening to, the roar, which is here, can be actually related to the Mach number, so how supersonic the jet was, and what it was overall the speed of the jet when leaving the vector. Now, let's change a little bit. Let's go and look on how the pyroclast move. And we will start from small end member of particles of pyroclasts. So volcanic ash particles. Volcanic ash is by definition any pyroclast smaller than 2 millimeters. Oh, I'm seeing that you were hearing things. Good. Thank you very much for the feedback. So now volcanic ash is particles that are smaller than 2 millimeters. And on a short time scale, they are really adverse impact for humanity. For instance, they are bad for agriculture because they cover the crop and they ruin them. And they are bad for farming, of course, because they are basically killing the animal by taking the food out of them and also giving disease to them. But they can also give diseases to humans because they can have particles smaller than 10 millimeters, 10 microns, sorry. They can be breathable and they are bad for your lungs. And they're bad for buildings, imposing an extra load and sometimes causing a roof collapse, for instance. They're very bad for air traffic and road traffic because just a little bit of ash makes any paved surface very slippery. So you have to close the highways, you have to cross the runways, but also volcanic ash can be ingested in jet engines and turn them off. And it's bad also for power and communication line because it can cause shortages, especially if wet. And it's bad for water and the water waste network because it's pollute them and just plug them. And it's bad for climate because big eruptions can cause global cooling for several years. Of course, on the long time scale, on the geological time scale, volcanic ash is the global fertilizer, so it's good for us. Small size of the ash particle implies that just a little amount of turbulence is enough to keep them in suspension for a long time. So in this satellite picture, we have ash being emitted from Etna over here and reaching the north coast of Africa over here, which is actually not a long trip for ash particles. But if you look at the situation right about here, where the city of Catania is, you look at something like this. At that time, just a few millimeters of volcanic ash were really enough to cause a big mayhem, with traffic disruption and a lot of economic damage. And similar locations around the world, in close proximity to permanently active volcanoes, experience a similar situation monthly. It's good to see that the cleaning technology, however, improves over time. The Japanese street ash cleaner, so actually it's spreading more ash than what is cleaned. And critical to understand the transport and deposition of volcanic ash is the terminal for the velocity of the ash particles under different conditions. So here we have ash settling down from a nice pumice volcano. And how can we measure the terminal velocity of ash particles? No surprise, using a high-speed camera. So this is a high-speed video at 1,000 frames per second. We collected under the plume of the Eyjafjallajökull eruption of Iceland in 2010, and you can see particles falling down. And we can measure the size and the velocity at which these particles are moving. And then when we started to look at this video that we took actually for scale, we noticed that something weird happened. So the particle seems to disintegrate when you heat. And this is because these are not ash particles, but are ash aggregates. So aggregates of smaller particles, bunches of particles adhering to one another and settling together. This is an important point because, as we were saying before, the balance of body forces, so basically gravity, and surface forces, so basically drag, is what control the terminal velocity of one particle. And what keeps the ash in the air is the turbulence. And as long as the turbulence, so the vertical component of the turbulence actually is stronger than the settling velocity of the particle will stay in suspension. In a volcanic plume like this one, the turbulence is very strong next to the vent, and then it decreases away from the volcano as the plume gets more dilute. And so what does it mean? It means that a bigger particle with a higher terminal velocity will settle closer to the volcano, while smaller particles will settle farther away from the volcano. But what happens if for electrostatic forces or, for instance, the presence of moisture makes the particles stick together? Then we have a larger particle, effective particle, with a higher terminal for velocity that will settle much closer to the volcano than what the individual particles will do. And we can measure this with a high-speed camera. because we can measure the settling velocity and the size of the particles. And these points here were the particles that were setting at that point. But for the same settling velocity, we can see much larger objects that are particle aggregates. And in this way, we were able to discriminate how many of the particles that sedimented at that location under the plume were actually particles and how many were aggregates. And as you see, there is a tenfold amount of particle settling over there due to ash aggregation. And tenfold increase of particle sedimentation means 10 times more particle that you have to remove and 10 times more particle that you can breathe. So it's a big deal. Now, volcanic ash being so fine-grained and with a regular shape, it's very easily removed by wind. And here you're looking at ash devils. And the remobilization of ash after one eruption is not a small local factor, but can be a big factor. So here we have a satellite picture and the numerical simulations of resuspension events in Argentina. So the ash was actually removed after months after the eruption from an area which is not very small, but still much, much smaller than the area that ended up being covered by a volcanic plume months after the eruptions. And to forecast this event, it is really important to define what are the conditions, under which conditions the volcanic ash will be prone to resuspension. And how can this be done? Best way is to use, of course, a wind tunnel. So we collected the ash from several eruptions and we brought it to Denmark to this fantastic, world unique environmental wind tunnel at the University of Aarhus. Actually, this is designed to simulate conditions on Mars, but we perverted volcanologists used it to understand how volcanic ash is suspended. And inside here, you can change temperature, and more importantly, you can change humidity, and you can change wind speed, and you can measure how much the wind speed must be to suspend volcanic ash from a sedimentary deposit. But there's one thing that we cannot do with this very sophisticated wind tunnel, and is to see the effect of local features. So we cannot have a pristine fallout deposit inside this tube, and we do not have the pristine substratum on which the deposit accumulates, on grass, on rocks, or for instance, a parking lot in Japan. And so what we did is to take a rather simplified version of the wind tunnel, powered by a leaf blower, and bring it to an ash-covered parking lot in Japan. So using both instruments, we were actually able to see the detachment of ash. So this is a front view of our mini field wind tunnel, where you can see in real speed the resuspension of the ash of the wind. And over here we have a time lapse showing just in a few seconds what happens over minutes. So the formation of sedimentary structures in our test bed. And then with the high-speed videos, we can actually measure the saltation and the detachment, the proper term, of the particles from a pristine ash substratum. What we're going to measure from this is something like this: the amount of resuspended ash as a function of friction speed, which is basically the shear stress imposed by wind over the deposit, as a function of what? As a function of particle size, and also as a function of humidity. When we see our results, is here what we look at. So here we have the particle size versus the threshold friction velocity. Basically, is a proxy for how much the wind must be strong to remove the particles. And what we see first is that, contrary to what may be expected, in this size range, smallest particles are the the smallest particles are the hardest to remove. And this is because the cohesion forces, electrostatic cohesion forces at this scale are much, much stronger than gravity forces. Of course, this doesn't work with boulders, but with small particles, adhesion by electrostatic forces is much stronger than adhesion by gravity. And so here, the smaller, the very fine ash, the one that is dangerous to breathe, is harder to move than the coarser one. And this is good to know for our health. Even stronger, the electrostatic forces are capillary forces. So basically wet ash is really, really hard to move. And you can see here where these cold colored points represent ash under wet conditions. So you see them as very harder to remove than the dry particles. Now we're almost there, and in the final part of the talk, I want to move now to the larger member of volcanic particles. And the larger member of volcanic particles, of pyroclasts, is volcanic bonds. Volcanic bonds is a definition for everything which is above 63 millimeters. But we will talk about particles that are even larger than this now. And the proper name for them is ballistic volcanic projectiles. And these are the killers for people who may be found in the proximity of volcanic vents. And these involve tourists that go visiting many touristy volcanoes, places where you can usually and safely see beautiful volcanic eruption, but that sometimes can have stronger explosions. And also these are the killers of, more importantly for me, volcanologists that works on active volcanoes. For instance, in this picture here, you see my usual field office, which is a Stromboli volcano. And there are a few notable things in this picture. So here in the background, we have these weird buildings, and these are specifically engineered shelters that are designed to protect tourists. So in the good season, we have hundreds of tourists visiting Stromboli every day. And usually the explosions are very safe, but sometimes we have stronger explosions, like those ones that throw bombs up to here. And we want our tourists to be safe, and also our volcanologists to be safe here. And the other noticeable thing in this picture are these. And these are volcanic bombs that have been ejected by a stronger explosion, and some of them rest inside their beautiful impact craters. And our volcanologist colleagues over here, they went right after the explosion to sample the ejecta from the explosion, and also to measure the size of the bombs and the size of the craters. And why this is important? It's important because those craters remain in the geological record and can be used as a proxy for past eruptions. They can use it as a proxy for the ejection velocity at the vent, because you can invert the distance and the size at which they fall for the velocity at which they were accepted at the vent. And they can even use it as a proxy for density of atmosphere, which is maybe not very relevant here, but was used to derive the density of the atmosphere on Mars. The point is that to invert the size and position and size of crater of ballistics for what was happening at the vent, you need a lot of assumptions. These assumptions can be verified again by high-speed video. So here we have high-speed imaging of a ballistic bomb, a volcanic bomb, while it's flying up and down and spinning. And you will see how this spinning is announcing the rebound of it when it hits the ground and the formation of multiple craters. And you will also see how a harder substrate changes the dynamics of landing on bombs. So there we go. That is really a nice rain of volcanic ballistic projectiles. You don't want to be there when it happens. So from these videos, we can measure, of course, several things. So we can measure the velocity of the pyroclast at their ejection, and we can measure the size of the pyroclast, like in this case, the main size of the three axes that we can look at. And we can also measure the shape of the pyroclast. In this case, it's expressed as the aspect ratio, so the ratio between the longest and the short axis of the pyroclast. And we see that we film a pyroclast between basically 10 centimeters and 1 meters and 1 meters per second to a bit more than 100 meters per second, and particles that were between equivalent to very elongated particles. So why size and shape? Because of what we were saying also before, body forces versus surface forces, inertia versus air drag. And air drag is in fact very important when it comes to control the motion of ballistic projectiles. And assuming that volcanic particles are simple spheres or blocks, it's not close to reality sometimes. To you, a golf club-shaped volcanic ballistic projectile and a bolas-shaped volcanic ballistic projectile, and the three bolas-shaped falling down volcanic ballistic projectiles, and my favorite one, the ballistic hula hoop projectile, my favorite pyroclast in the planet, probably. And then there are other things that can affect a theoretically ballistic trajectory. For instance, one thing is that those particles are often looked at breaking up while they fly. So here we have one particle which is breaking by stretching. And this is an all effect, a secondary fragmentation process beside the one that involved magma as a whole. This process is changing the grain size of particle that we are seeing in the end in the and this may happen not only
We're back.
I'm back again. I don't know what happened.
It's the joys of being virtual.
It went ballistic. Okay. It was almost over. I think I just gone and so let's try like this and let's see what happens when I go to PowerPoint. It was meant to happen, come on. It was going too well. Okay, I think we are there again. And I was showing, okay, ballistic colliding and bouncing. And I was just about to show you, I think, ballistics colliding and getting fragmented by the collision in between them. And all of those things are important because they change the trajectory of ballistic particles. And okay, let's move to the next slide. And well, okay, this is very quickly just a 3D filming of the ballistics. So what we did was to use two high-speed camera filming an explosion of an angle in such a way that we could have a 3D and not just a 2D video of the explosion and follow the trajectory. And with a high-speed camera, we can track the bombs, and so we can reconstruct the trajectory. In this plot is just the reconstruction of part of the trajectory of 9 ballistic volcanic projectiles. And so the trajectory starts here with the small balls and end up here with the large balls. And the ball color is proportional to velocity. So this is faster and this is colder. And on the top line over here, we have 3 very well behaved volcanic bombs. So as you would expect, they slow down while they go up, and then they reach a minimum velocity, so 0 vertical velocity, but just horizontal velocity at the apex of the trajectory, and then they accelerate again when they start to flow down. But down here, we are the badly behaving volcanic bombs. Bombs that do weird things. For instance, this one started slowly and then accelerated even more again. That shouldn't happen. And also what we see is that we have trajectories that are changing quite drastically. So all these weird behaviors are due to either collision of the bombs in between the gel itself or tearing of them, or also deformation or reorientation of weirdly shaped bombs. Those things are important because when you do a numerical model and you impose some initial condition of an explosion, you want to know where the pyroclasts end up, then you must account for those things. And there are also other things that you must account for. For instance, the Magnus effect. So I was with the Magnus effect, that makes the trajectory deviate. And the most important thing is that we can measure the drag coefficient of the particles. And the drag coefficient is what's related the shape of the particles to their velocity and the drag force that is exerted. And so basically drag coefficient is fundamental if you want to calculate the range at which a projectile goes if you know the exit angle and the exit velocity. And what we find interesting is that the values that we measure directly on the field turn out to be a factor 2 to 4 higher than what is usually used for numerical modeling. And this is important because it means that if you do an hazard assessment map, for instance, you are overestimating the range of the particles, or you are underestimating the ejection velocity if you're inverting it. I'm done. The only thing that I wanted to say is that all pyroclasts that are born by breaking of magma end up at rest in a pyroclastic deposits. And scientists have been using pyroclastic deposits for centuries by now to understand how the volcanic eruptions occur and how they happen. And me, for instance, I started my career mapping pyroclastic deposits and doing thin sections. And once I was talking to a colleague, and I remember like boasting over how much my career had changed over time, passing from field mapping to now using high-speed camera. And he was saying, no, no, you're still doing the same thing. You're still looking at pyroclasts, but now they move while you're looking. And that's all. Thank you very much. So I stop sharing the screen, and I don't know what happens now.
Okay, thank you for such a great talk. It really was a blast. It was great, thank you. We have a few questions from the Zoom, from the Discord chat, so I'll ask some of them now. So the first one says, would the angle at which the wind hits the ground, i.e. different angle at which the shear stress is applied, change the resuspension of the ash?
Yes, yes, there are, of course, local factors that are important. So basically, over the atmosphere, you have a boundary layer, which is hundreds of meters thick, and that sets the wind direction locally. And then you have the smaller scales, irregularities, and also this changes the local wind. This is why what we were testing was not actually wind, but it was this threshold friction velocity, which is the shear stress which is imposed on the particle. And this varies locally, and you all can have experienced this. If you walk, for instance, in any landscape after a snowstorm, you see that the distribution of the snow is being changed by the wind. And there is a snow accumulation in some places and erosion of snow in some other places, all due to the local distribution of wind.
Yeah, so another question we've got from the Discord is, ash aggregates seem to make a lot of difference on the fallout from volcanic plumes. What would these ash aggregates look like in the rock record? Would we be able to look at an ash layer and be able to tell these were aggregates, or do they fall apart on impact?
Excellent, excellent question. And there is all range of ash aggregates. The largest one are accretionary lapilli, and they can be as big as my thumbnail, and they are easily recognized in deposits hundreds of millions of years old. So they are very well preserved. But for instance, the small aggregates that are kept together by electrostatic forces, they are almost never preserved in the record. And sometimes you have, so the deposit that we were sampling at Eyjafjallajökull, the ones that we were actually filmed, didn't look at all like they were sedimented as aggregates. What happens is that when you go to the record, what you can see is that the particles are weirdly fine-grained with respect to what they should be, or maybe with respect to what they are around the deposit. Because the single particles, they look like single, but they were sedimented as aggregates. And then there is another broad range of anything from droplets of water with just a few particles inside to balls that disgregate and everything else.
Okay, we've got another one on the Discord, and it says, could the bad behavior of the bombs be attributed to the cooling of the material during flight, changing the ability of the bomb to deform with the applied drag? And is there an observation of this?
Also, this is an excellent question. We see the bomb cooling, of course, during the flight, clearly. I don't know if you noticed it in the video that I was showing, there were at one point very bright bombs flying up and much darker bombs falling down. And it may change their shape, of course. I mean, once they're cooler, they shouldn't change their shape much more. Although we have seen in-flight breaking also of cold bombs. And another factor that could be important is the temperature of the surface. It's changing the density of the gas, of the air, basically, which is around it. And this may change the aerodynamic properties. This is one explanation that we have for the fact that we measure drag coefficients that are higher than expected.
So we have one more, which is sonification of your data is really nice. Where did you get the idea to do that? And do you think it makes you think about its meaning in a different way?
I got the idea of sonification from Jörg Neuberg, which is a great geophysicist that was sonificating earthquakes. And a friend of mine and a PhD and volcanologist, Damien Godin, first did the sonification. And the point is that with feelings different that the sight, you can recognize things in a different way. And your hearing is much more trained to recognize fast variation in time and repetitions also. And actually, there's a whole science of sonification of data, of scientific data for blind people, basically. Thank you very much. All excellent questions, really.
Okay, thank you. We're going to have a quick 10-minute. Oh, we have another question into the Discord, so I think we do have time for that one. Says thank you for an interesting talk, and they wanted to ask whether crack propagation that occurs in the interior of the surveyed volcanoes informs the concept of transcrustal magmatic systems, whereby the cross-cutting networks of dikes that originate from a source in order to move magma via the interior geometry and stress fields to formulate volcanic edifices.
Wait a second. I'm trying to read it. Yeah. I'm reading it in Discord. And the crack propagating that occur in the interior of the surveyed volcanoes and the concept transcrustal magmatic. Ooh, I don't know. No, if I understand the question right, the point is, so I was talking about the cracks that fragment the magma. And the question seems more to me to talk about the cracks that form in the crust and that the magma uses to move inside the volcanoes, if I got it right. I don't know. I think there may be, but I mean, I will be very, very glad to talk about it by email or keep on Discord. So I'm here all the evening, you know, so I will be happy to keep on reading and chatting.
Yeah. So if anyone else does have any other questions, feel free to pop it in the Discord channel that we have, and Jacopo will be fine to answer some of them. We're going to take a quick 10-minute break now, and we'll be back at around 20 past. We'll be putting a message into the Zoom chat and the Discord to say when we'll be coming back for the next talk. Thank you.